In the videos you just watched, you got a strong example of a well-defined problem in the Monty Hall problem and an ill-defined problem with the bicycle helmet problem. So the Monty Hall problem, again, and I know that this is difficult to understand because it flies against most people's intuition. The Monty Hall problem is completely predefined. All the probabilities are known beforehand. And if I could take a second to try to explain it and see if you get it, if you didn't yet, each door, a priori, has 1/3 of a chance of having the car behind it and 2/3 of a chance of not having the car behind it. So in other words, from the start, your chance of picking the correct door is only 1/3. Your chance of picking a wrong door is 2/3. Now, once the game show host reveals one door with a goat, that means that out of that 2/3, he's actually showing you kind of the wrong portion of that 2/3. But the chance was still 2/3 for the car to be in that particular portion, and meaning those two doors. Out of the two doors, he has now eliminated one of them. So the remaining door still has 2/3 of a chance of having the car behind it. And this is why you should switch. This is completely well defined, right? Everything is known. All the options are known. All the probabilities are known. And you make decisions based on that to try to solve it. The bicycle helmet example is so interesting because there, as you saw, the first step was almost to even figure out what the actual problem was. And then they figured out that people didn't want to wear a bike helmet because it messed up their hair. And then they thought, okay, what if we can make the helmet only appear when people actually need the helmet for protection, meaning only if they fall. And then they figured out all the technology that they needed to build into this helmet in order for that helmet to appear exactly when it was needed. So these are two really nice examples of how well-defined and ill-defined problems differ from each other. Now, both of them can be related to the phenomenon of insight. And insight is this all of a sudden, this aha moment, a very sudden restructuring of a problem where you've been thinking about something in one particular way, and clearly that doesn't give you the actual solution to the problem. And then finally, all of a sudden, you're taking a shower, you've gotten some rest, you've put a problem to bed for a little while, you come back to it, and all of a sudden you realize, aha, if I do this slightly differently, then that will give me the right solution. And interestingly enough, this is known as an aha experience or a Eureka moment. And there's an interesting story from Greek mythology behind that. The Eureka moment came when, according to legend, King Nero had a golden crown that he had made from a goldsmith, and he didn't want to be betrayed, so he wanted to actually know whether the full amount of gold that he had given to the goldsmith had been used to create this crown, or if the goldsmith had saved some of the real gold off of it and used a much cheaper metal in the inside so that the crown was not fully gold, and he was actually, being taken for a ride, that the goldsmith would have taken some of the gold. So the question was, how can we figure out if this crown is fully gold or not without having to break it open to actually see? Because obviously you wouldn't want to destroy that crown. So King Nero hired a very smart man by the name of Archimedes. And Archimedes thought about it for several days and could not figure out how to determine what the crown was made out of without having to break the crown. And then one morning, he still was sitting on this problem, and he decided to take a bath. And according to legend, when he took the bath, he realized that as he submerged his body into the water, he noticed that the water level rose. And that's where he had his Eureka moment, or his aha moment. He realized right then and there that the amount of water that was being displaced by his body depended on the volume and the density of his actual body. And once he realized that, he thought, wait a second, what I could do is fill a bucket with water, then put the crown in it and catch all of the water that's now spilling over the bucket, and then measure how much water that is and how much density that is, how much volume. And from that, I can then deduce whether the crown and the amount of water actually corresponds to how much water should have been displaced had this crown been made out of pure gold. And if it's less, then I know, or if it's more, then I know that there's some metal that was used that's actually not the real gold. And that is in fact exactly what he found out. So according to the legend, he jumped out of his bath when he realized this, ran through the street half naked, screaming Eureka, and this is why this is called a Eureka moment. Now, people are not the only species who can have these kind of aha experiences. Interestingly enough, apes are known to be able to solve problems as well, and especially when they're living in the wild. So even in 1925, Germans were already studying monkeys, and they actually discovered that animals can actually engage in productive problem solving and not just reproducing a problem solution. So it's not just that they have a solution to the problem and now they just copy it, but there was first evidence in 1925 already that some species can actually engage in productive and creative problem solving. Sadly enough too, in 1945 already it was also shown that apes that were raised in captivity actually showed much less evidence of that ability to generate insightful problem solving solutions. So that's a sad part to it. And I'm going to post a video for you that will show you some evidence of apes being very smart at problem solving otherwise. Now, how do we study problem solving? Sometimes we give people these kind of artificial problems. So here's one of them. And in this problem, you're being asked to find a way for this person to have both of these ropes in his hand. And the way these ropes are positioned is such that you couldn't reach the second rope while you're holding the first rope. So you have to come up with some other solution to make this happen. Now you see that there's a couple of objects in the scene, pliers, a chair, some paper, and so forth. And in this particular problem, people need to start thinking about the objects that are available. So maybe you start thinking, oh, maybe if you put the chair in the middle, then you're higher up, then maybe you can grab both of them. That's not a solution in this particular case. That still doesn't work. And then after some time, people may realize that if they put the pliers at the end of one of the strings and now make the string swing back and forth like a pendulum, now grab the second rope, have that in their hand, and then the first one will actually swing right into their hand and they can actually grab both. So that's one solution where people typically sit on this for a while, and then there's sometimes an aha experience where they realize, if I use this object in a non-conventional way, right? Normally you don't use pliers to make a pendulum, but you could. The second they realize that, now they can actually solve this problem. Here's another one that's called the candle problem. You're being asked, okay, here's some matches, here's a box with tags, and there's a candle. How can you create that this candle is actually affixed to the wall and actually lighting a little candle? Well, here again, first you got to realize that you can use this box here as an actual little shelf to put the candle in. So the idea is this: you first empty the box, so that's empty. Then you light a match, you hold it underneath the bottom of the candle so that it starts melting. Now you can stick it onto this particular box almost like a shelf, and then you could actually pin the box itself to the wall so that now you end up with a little candle in a little holder. So these are the kind of problems that people sometimes use to study this. And the main thing that comes through in these sorts of problems, and the way people get stuck and then get unstuck, if you will, is that they have to overcome what's called functional fixedness. Functional fixedness relates to the idea that we think about objects in their most conventional ways. So for example, if you see a chair, typically you would feel that you want to sit on it. This doesn't mean, however, that if you get in a fight with somebody and you see a chair, you couldn't pick up that chair and then all of a sudden use it as a weapon, right? So sometimes people fail to realize that objects may have additional functions beyond the most conventional ones, and for them to solve some problems, they have to kind of let go of the normal use of something and then try to think of something in a slightly different way. And then the second they do this, they overcome their functional fixedness and they can actually move on. Here's another problem that's sometimes used to study insight, and this is called the mutilated checkerboard problem. Question here is that you get this board of dominoes, and you're being asked, can 31 dominoes, each of which can cover 2 adjacent squares, fill this mutilated checkerboard? So you see in this board that there's a piece missing here and a piece missing there, and you're being asked, is it possible to fill this whole board without one being left open or without one piece sticking out? And the key thing that can help you to fix this problem very quickly is that you realize that when you put down one domino, the domino should be covering a red square and a black square. If you then see which squares are missing, you see that there's a black square missing over here and a black square missing over here. And because of that, you can know right there that it's impossible to actually cover this whole board of dominoes fully. Here's one last problem, just for you to play around for a second. So imagine that you get this particular shape right here of these dots, and you're being told that you need to turn the one on the left into the one on the right by only moving 3 of the dots. Okay? And you can sit on this for a while, and if you want, you can pause it and try to do this for yourself. Key thing here is that you realize that rather than starting to move things up from the bottom, which will not get you to this in 3 different, in only 3 moves, the key thing is to move the 2 on the side here all the way down. So this one goes over here, this one goes over there, and then after that you grab the bottom one and actually put that all the way on the top. And that's the only way to actually get that done in 3 particular moves. Here's one last one that I had already talked about when I started talking about problem solving at the very beginning of the course, right? What if you have to connect all of those 9 dots by drawing no more than 4 lines? Key insight there was to go outside of the box, literally thinking outside of the box, so that you kind of extend the first line past the edges of the box, then the second line can move through, third line can move through, and then the fourth line actually manages to cover every single one of them. So that is just some examples of some problems that are being used when people study this. In the next video, I'll start talking about some theories about how problem solving then actually works.